So this is actually an interesting anniversary event. So exactly 7 years ago, in 2010, the very first presentation of the Netflix architecture was at QCon San Francisco. And it was right here, and I'm not sure we're in this building, but Randy Shoup was doing the architectures you've always wanted to know about track, and he'd been to QCon the year before. It was my first time to come to QCon, and I came and I explained what we were doing and pretty much baffled everyone in the room, I think. So it was, people thought we were pretty crazy at that point. But it was, this is a great conference. I really like the way QCon is run, and it's always been one of my favorite events to go to. So I'm going to run through a whole bunch of stuff. And I'm going to lead into chaos architecture, but first of all, I'm going to talk a bit about what's going on in kind of the evolution of business logic as we've gone from monoliths to microservices, and then talk a bit about the cloud-native principles. Since I got 50 minutes, I'll sort of do some intro, and then about halfway through, I'll switch over and start talking about how we can think about applying chaos architecture, chaos engineering to these cloud-native architectures. And I call that chaos architecture because architecture is cool, right? So, business logic started off pretty monolithic, and then we came up with these nice microservices, and now we're transitioning to functions. And so I'm going to go, why did that happen? So the thing is that if we go about 10 years ago, monoliths were the thing. That was what we built, and we built it from good reasons, because the networks we had were slow, and the interprocessor communication we were using was mostly XML and a bit of SOAP and all those nasty things. Some people are probably flinching or twitching hearing about this stuff. It was big and heavy and slow, and if you tried to divide your application into lots of pieces, you divided it into two and you were pretty much stuck, because by that point it took too long to respond. So the problem was that it was too inefficient to break everything into real chunks. So we had service-oriented architecture, but the services ended up as big, monolithic, bundled-up services that did too much stuff. If we tried to break it into the individual, like, single-function level components, it would run too slowly. So there were a few attempts to do true SOA. Most of those just, like, died because they couldn't keep up. So then, about 5 years ago, we sped things up a bit. We have 10 gigabit networks instead of 1. That helps. We have JSON, REST. We're actually able to break our application into chunks which are kind of do one thing at a time. Right? You get your bounded context now is a microservice that does one thing. It's got a few upstream consumers, a few downstream dependencies, and you really want to just have a single thing that it tries to do. Right? And that means they're more testable, they're easier to reason about, they're easy, when they go wrong, it's much easier to figure out what went wrong, because this one service that does one thing is behaving strangely. So that is part of the whole sort of migration here. And then we get to, this is actually a simplified model of one of the sort of, by the time we got to Netflix, we were building things like this. This is to just service the homepage. That was kind of, there's an API call at the end or something, and there's a whole bunch of stuff going on, and the things on the right-hand side are the storage-based services, and the stuff in the middle is all the different stages in between. So we're building these microservice systems, and then we started noticing that a lot of these services that we were building, that were like one corner of the monolithic application was a library that did some queuing thing. And now we built a microservice that just does queuing. Then at night, well, we don't need to build that service. We can just run it as a thing. So we start migrating to have standardized services. So a lot of the off-the-shelf pieces turn into standard services. So you start using SQS because it's a queue and I don't have to implement it. You start using Kinesis because I don't want to have to run Kafka and scale it and figure out how to do that. I can just call Kinesis and all these other different things. So you end up building a fairly large chunk of your application that used to be embedded in this monolith and then got broken out has now become whittled away. So what's left in the middle is the business logic, which is the thing that actually you were trying to build in the first place. So there's less work because there's less stuff to write, but you've got more dependencies around the edge, okay? Now these business logic, we started to break into individual functions, and this is kind of where we get to the serverless model. Because now instead of having the same functions built into each microservice, we just implement it once and you just pass events back and forth between them. So this is starting to come along. But the way I've drawn this, they're all sort of grayed out, right? Because they're not really running. And the interesting thing is that when something comes in, it wakes up these services, and you only wake up for the things you need, and then they go away again, right? So this is pretty high level. I know most of you know how serverless works, but like this, I give this talk to sort of managers at big companies so that they try to understand what serverless is. But the real point here is that when the system's idle, it shuts down. It costs nothing to run. And that's why we're tending to see huge cost savings with this serverless architecture. And there's much less code to write, so it's actually faster to write. And you're gluing together building blocks that are already scaled and reliable, SQS or something. So you're writing less, and it tends to work and scale more easily and cost less to run. So there's this double win here, that it's faster to write and cheaper to run. And we're seeing that's one of the reasons I think serverless is particularly interesting. So there's different cases. If you hit a serverless function enough times, you kind of want to run it permanently rather than invoking it every time. So let's look at cloud-native architectures, and I'll talk a bit about the principles here. So what do we mean by cloud-native? Well, let's think about data center native. You have a data center, and every now and again you send another rack of systems into it, and the systems sit there for years, and but what you really wanted to do was shift it out of there and put it up in the cloud. So there we go. I have a company that, this is the best thing about my new job, I have a company that makes slides for me. And I said, make a forklift truck go into the cloud, and they came up with this. It was brilliant. My graphic art skills are woefully inadequate, as you can see by looking at any of my older decks. Yeah, this is cool. So the point here is that instead of paying up front and depreciating over 3 years, you're paying a month later for the number of seconds you use. Because I don't know if you noticed, a month or so ago, we stopped charging by the hour. Now we charge by the second. You have to pay for the first minute. After that, it's per second. So we've now got really fine-grained for instances. Lambda functions are per 100 milliseconds. So you're really consuming just what you need. You just have to get good at turning stuff off. So the point here, this is the first principle. Pay for what you used last month instead of what you guess you're going to use next year. All right, so that's the first thing. Now let's think about how we get there. Old world, you file tickets and wait. But what you really want to do is make it self-service, on demand, just make a call. And then, sometimes somebody's out having a coffee or at lunch and nothing happens to your ticket, but you can just keep calling this service, everything happens. So what we really wanted to have here is deploy and do things by filing a ticket. And you don't want to do that. You want to make an API call, self-service, just get stuff. And that is the other kind of benefit of these cloud-native architectures, right? That they're demand-driven, self-service, automated. And instead of moving from lots and lots of tickets, you want to move to having a tracking ticket that records that you did something, but you're not asking for permission. The ticket isn't asking other people to do things. So your ticketing system turns into like one ticket per deploy, which records the stages that deploy went through as it happened, right? So you've got your audit trail, but you're not, maybe if you're deploying a new finance system, there's some manager has to sign it off to say, yeah, I approve this update. But that's generally, you can get down to a single approval for a deploy. And that's sort of the current state of the art. Now, if you're trying to get there and you're going, this sounds like an alien from another planet and we have this nice waterfall that takes a year, what I recommend people do is measure the number of tickets and meetings per deploy. Right? And write that down and make a little graph of it, and then tell people that this is a bad thing and make the numbers go down, right? So that's a sort of a strategy for exposing the fact that there are so many meetings and tickets, and you want to have less, and you can drive it down over time. Right, so that's another principle. So here's another one. We've got all this infrastructure scattered all the way around the world, and if you want to deploy something in Latin America or Japan or Germany, it's just a different drop-down on the menu, and you just go and do it, and that's cloud native. Whereas if you want to build a data center in Brazil, anyone that's ever shipped hardware to Brazil knows how hard it is to do that. I mean, some countries are more difficult than others, but whatever it is, you've got to hire people and find a building, and it takes a long time. But it's a drop-down on a menu. It's no difficulty. It's no harder to deploy in another country than it is to deploy in your own country. So this is another principle, that you get to build instant, globally distributed applications by default. If you want to do some long latency testing, set up a machine in Oregon and a machine in Dublin or Frankfurt and run the test. it's no harder than setting up two machines in the same region, right? So this is another new principle. All right, so if we look at an individual couple of regions and the sort of typical data center architecture, going to get a bit topical here. Let's have a hurricane. Hey, Hurricane Sandy comes in and floods New York. Been lots of hurricanes this year. So you fail over to Chicago or something. But the way we build it in the cloud is we have regions with zones in them. The zones are between 10 and 100 kilometers apart, so they're not in the same floodplain, they're not in the same blast, fire area. They're far enough apart, but they're close enough together for synchronous replication. That's why the zones are are no more than 100 kilometers apart, right? So you write stuff, you want it to go to all three zones, you don't have to wait. But across regions, there's more latency. It's typically asynchronous, right? So if you do a data center migration to cloud, and let's say you have a MySQL primary and secondary, and you just copy the image that you had in the data center to the cloud, you're only using one zone. You haven't really got any additional resiliency here. I wouldn't say that's a cloud native thing. It's like a forklift. What you really want to do if you're moving from a data center is replicate the data across, like replicate copies of your application if it's horizontally scalable, replicate the data across three zones, and then you've got a much more resilient system. And if there's another hurricane comes in or something, it might affect one zone, but it's very unlikely to take out all the zones in a region. So it's more inherently resilient. So another principle here is you should distribute over zones in a region by default. All right, let's talk about elasticity. It's pretty hard to get above 10% utilization. I tried that on somebody earlier today and said, yeah, ours is like 8%, right? That's their average data center utilization across all time. And in the cloud, I think you should be targeting, you could argue the numbers, but I think probably 40% is plausible. You kind of want to average, target 50% and overall average, maybe you'll get 40%, right? But it's many times higher. And you don't run out of capacity because you just scale up more, right? So the effect here would be if you had 1,000 machines in the cloud on average, right? And your average capacity in the cloud is 1,000 machines. You'd need 4,000 machines in the data center to do the same workload. That's the 4-to-1 because you're running these machines 40% busy, these machines 10% busy. That's the same capacity, right? Except the cloud, if you need 10,000 machines, you can go get them. So you want to auto-scale predictable heavy workloads, because you're going up and down. But for the lighter workloads that go all the way to 0, so if you're looking at, I want to deploy across zones by default, that means I need at least 3 machines of every type. In fact, the pattern at Netflix, we said we want at least 2 machines in each zone. So our minimum deployment was 6 machines. And you could get fairly small machines, but it's still 6 machines. And if you have something that doesn't need 6 machines, you should use serverless and just go down to have, Lambda just create the machines when you need them. And it's a lot cheaper. Okay, so here's another principle. Turn it off when it's idle, many times higher utilization, huge cost savings, and it avoids capacity overloads. Okay? All right, let's just have a quick look at the way deliveries are done in the cloud. Developer builds something. You want your time to value to be really short, maybe a day. I'd say state of the art right now is you write some code, you develop a function, you say, okay, this is a good change, you hit save, you save it into your build system. It should go build it. It should deploy it. It should put it in a canary test to see if it looks good. And by the time you come in to work the next morning, it should be deployed in at least one region. And maybe over the next some period of time, it deploys globally. But that's kind of, I'd say, state of the art for time to value. I wrote a line of code. How soon did a customer get some value for that code? That's a day, right? Some people, this is years, right? But I think a day is good. It's probably, you could go faster, but that's, I think, a reasonable thing to do. But the point here is that you're keeping old versions of things and that you don't replace the previous version of the system. Like this was the old way of doing it where it's so hard to get get VMware to give you, somebody to push buttons on VMware to give you a new VM. It took you months to get. Once you got it, you would update it. You'd use Chef or Puppet or something to keep updating it. So you do replace in place when you were doing things. Whereas here, it's like I can get a new machine in a minute, so I'll just get another machine alongside the old machine and run side by side. So now you can run multiple versions at once, and you just need to be able to route the traffic between them. So here's the other principle. Immutable code, automated builds, ephemeral instances, containers, and functions blue-green deployments, and versioning your services. Okay, so that's kind of what I mean by cloud native, and this is the full set of principles just to revise them, right? So paying as we go, self-service, globally distributed, cross zones and regions, high utilization, and immutable code deployments. Maybe other things, but if you're doing most of these, I think you've got a cloud native application, and if you're not, you're probably just forklifting some data center stuff. All right, so I'm going to move on now and talk a bit about chaos architecture. And I like to describe this as 4 layers, 2 teams, and an attitude. So I'm going to go through and explain what these layers are, kind of what the teams do, and what the attitude is. First of all, infrastructure and services. You basically want to set it up with no single point of failure. And you've got all of these zones around the world and regions and whatever. It's easy to do. But what it really means is you get this region and you deploy multiple things. And if you zoom in on that, you see everything's interconnected and you've got multiple versions of it. And you zoom into one of those and there's more versions and you've got more zones. So you're using lots and lots of replications at multiple layers as you go in. But the key point here is you're just trying to get to have no single point of failure. And what I really mean is there's no single point means it has to be distributed, right? If there's no single point, that means you're building a distributed system. And if there's no single failure, it's got to be a replicated system. So we're building distributed replicated systems, and we want to automate them. And cloud is the way that you build that automation. So what we're talking about here is systems of distributed, replicated, automated cloud. And that is how you can go and deploy something that is going to give you the infrastructure reliability that you need. All right, so that's infrastructure. So there above this is a lot more interesting. I call it the switching interconnect level. Because if you've got data in more than one place, you have to figure out how do you get the data there? How do you keep it in sync? There's some data replication going on. There's routing between where you get customers or traffic has to be routed to more than one place. Because if the place goes away, you've got to route around it. So let's just sort of show a little diagram here. So this thing went away, and those customers get routed somewhere else. Okay? So that's traffic routing, avoiding an issue. But then, and I was telling someone earlier in the previous session, we had years and years ago, I was at eBay, and we had a data center outage, and it was a big scramble to get it to fail over. It took about a day or so to get everything back up, and then it took a month to fail back afterwards, because we didn't know everything after the failover was such a mess that we couldn't actually figure out how to get it back safely. There wasn't a simple switch there and switch back. So this is, if you fix it, you've got to go put all the customers back in, and then you go to this anti-entropy recovery. You've got your data's now out of sync, so you have to resynchronize it, and that's typical anti-entropy algorithm. So I'm going to ask a little question here. Who here has a backup data center? A backup data center? Okay. What's the best description of it? Is it availability theater? You've never, ever failed over to it? Right? It's usually, I get some good embarrassments there. If you're trying to sell chaos engineering to your management chain, see if you can get the CEO to ask the CIO if they've ever failed over to their data center, their backup, right? That's one of those embarrassing questions that will cause them to go fund a chaos engineering team. That's a theory anyway. Try it. Or infrequent partial testing. App by app, you do a failover to the other data center. If you do that, you can kind of get, there are some compliance rules and industry regulators. That's kind of the minimum to pass audit if you're a bank or something like that, right? If you do individual failovers. But, or regular tests during maintenance window. So at the weekend, when you're not doing anything, you actually do an entire failover to prove that you know how to do it, and you exercise. People do that. Some people do that. That's kind of a good practice. Or do you do frequent failovers in production to prove that, and nobody can tell you're doing it, right? And we're hearing from Dave Hahn, sort of every week or two, Netflix actually shuts down an entire region and moves all the traffic somewhere else. It takes them less than 10 minutes, and nobody notices it's happening. And if it fails, they do it more often, right? This is that continuous delivery principle that Jez Humble came up with. If it hurts, do it more often. Have you heard that? So the point here is if you keep doing this frequently enough, it will stop hurting a norm, and you just end up with, if there's some issue in any part of your system, you just switch away from it and everything's fine. So here's the problem. You want to route updates and customer requests to specific regions and services. You want to replicate data and reroute requests during incidents. And the switching mechanism, this is the hard part, needs to be more reliable than the things you're switching between. This is one of these principles of highly available systems. If you put a switch between two things, the failure rate of the switch has to be vastly better than the failure rate of the things. Otherwise, you're just making it worse, right? The combined reliability of the whole thing is dominated by the fact that the switch is less reliable than the things you're trying to switch between. And what we find is many cases there are these, you get some small failure in your system and the system starts to respond to it and then you say, let's fail over, and then it turns into a massive outage because everything collapses and all your switching software. You find every error code path that hasn't been tested in your system, right? That's the problem. So the only way you can exercise those error code paths is by regularly running these tests and exercising it, and that's kind of, I keep going on about Netflix, but they really are state of the art here. I don't know many people that are doing that frequent failovers. I heard of a bank once that flipped every weekend, so like even weeks you're on this data center was the primary, and odd weeks this data center was the primary, and they just flipped back and forth every weekend, and if there was a problem midweek, they just did the flip and kept going. That's, I think, a good state-of-the-art way of doing this, if you're in that kind of environment. Okay, so that's the switching layer. Let's move up a layer, applications. So what happens if the application gets an error it wasn't expecting, or it gets a slow response, or the network connection drops? Does it crash? Does it fall over? Does it write the wrong data to the wrong place? You see all kinds of nasty behaviors. So that's a bit of a problem. We'd like to be able to test these things better. But with microservices, it actually gets a little bit easier. Because with a monolith, it's really hard to test because it does so many things that it's got so many conditions that it's basically going to be difficult to test all of its error cases. But a microservice that does one thing, it takes one input and it gives you one output and it has a bunch of dependencies. You can basically reason much more about what it's going to do. You can put circuit breakers in there to limit that data source. You can have bulkheads to prevent it spreading. There's an architecture. There was a talk, and I think it might have been the QCon London event. I think it was QCon London from Starling Bank. I think Starling Bank did a nice talk. And I helped review the thing, and he had this incredibly long acronym for his architecture, and I noticed that part of it was ditto. So this is now the ditto architecture. Do idempotent things to others. So it means that all of your requests are idempotent. It means you can do at least once delivery of everything, which means that you can multiple deliver and it doesn't matter. And all of your transactions become nicely behaved events, and that way you can scale. It becomes incredibly resilient and reliable. You can reason about the system. If you have something that has to be delivered exactly once, you've built a system that is going to have trouble being available, because you have to, if you're not sure if it got there, you have to kind of freeze the system to figure out what's going on. That's the kind of consistency problem of exactly once delivery. If you can set it up to always be able to multiple deliver and not have a problem, then you can deal with it much better. And so really what we're trying to avoid is avoid update and delete, right? Those change the state. Append and write are fine. You're just appending a write log. So you just build these logs of what's going on in the system and the current state of the system. If I can see all the logs, I can figure it out. Right? This is basically double entry bookkeeping. It's a 4,000-year-old algorithm invented by Babylonians with clay tablets. And seriously, it's one of the oldest algorithms, and it's because they couldn't rub out the clay tablets. You just had to append, right? So the reason that we have update and delete is because computers were too small a few decades ago, and there wasn't enough memory or disk space, so we optimized by updating stuff in place. Whereas if you're doing anything that matters, you should just build logs. Just keep logging. Maybe you purge it every now and again, but update is a terrible thing, because if you're caching and pointing to something and it changed, you didn't know it changed. Right? That's the problem we're trying to avoid. You delete by writing tombstones over things. This is sort of the Cassandra way of doing deletes. All right, so that's the application. People. We've all seen this, right? System's fine. It starts behaving slightly strangely. and you go in and go, why did it do that? You start rebooting bits of it, and if there's a knob, you turn it the wrong way. If there's a button that says do not push this button, you push the button. And people will screw up a perfectly good system that's very highly available. And there are lots and lots of examples of this in the real world. And so what are we going to do about it? We have to train the people. And I have a nice analogy here. How many people here have never had a fire drill? Like pretty much anybody that's ever worked in an office has been through a fire drill where you go and stand in the parking lot for 10 minutes while they count everybody that got out and make sure everyone got out of the building and make sure no one tried to use the elevators and all that kind of stuff, right? We know we're supposed to do this. And then every now and again there really is a fire and it saves lives. And like just before the first time I gave these slides, there was a huge earthquake in Mexico. And 2 hours before the earthquake, there was a public earthquake preparedness drill in Mexico City. It's like everybody in Mexico City was trained in how to respond during an earthquake 2 hours before the real one happened. And you know it's a real one because the earth's moving a few feet side to side underneath you, right? It's not just, hey, we're sending off a siren, right? But here's the question, right? Who runs the fire drill for AT? Right? If your infrastructure and your applications are on fire, what are you supposed to do? You didn't train everybody in how to respond to that. So this is where I think that is one of the sort of prime functions of the chaos engineering team. And I've got a link to the Netflix authored book on this subject. You've got people, application switching, and infrastructure, and the chaos engineering team's job is to build tools which exercises all of those layers. And here's some of the tools. So there are people running game days, so that it's exercising what to do during an outage. Can you find all the information you need? Do you know how to be on a call, on the con call where we're discussing the outage? There's a set of behaviors there that work. If you don't know what you're doing, you can actually disrupt the call. And there's, an efficiently managed outage incident call is a really powerful way of getting the outage to be really short. And if you don't, you can make it worse. The Simian Army, there's all of the open source and the chaos monkeys and things like that. You're building failure injection tools that can put things in the right place. And the chaos automation platform, CHAP is Netflix, there's a blog post on it, which is basically they're automating their failure injection, then they're automating the process of choosing where to inject failures and the operation of those failures. And if you start noticing that your failure test is causing a customer visible problem, then you back out of that. And then Colton's built Gremlin, which is sort of a productized version of this. So you can go find a Gremlin and go. And I still don't think you have a competitor out there. So you're a category creator. It's a brave place to be in a market. But I think we need more tools here. There is actually, Russ Miles is doing chaos.io. There's a GitHub account. They're starting to build some open source pieces that start to do little bits and pieces of this. So I think it's an interesting time. And if you want to get involved in building stuff, this is a great opportunity to contribute open source tooling and concepts and ideas. It's a really emerging area. But there's another team that does something similar. And some of you have security teams to protect your systems, but the more advanced companies have a red team whose job is to break into your systems to prove that the security team's doing a good job. Right? You heard a lot about this from Shannon Lights at Intuit. Go watch her presentations on this. Red team comes in every Monday morning and just breaks into all of the stuff at Intuit because all the stupid things developers did last week, right? We'll go find every buffer overflow that got introduced and every whatever, and they get into the system. So they build tools. There are tools for this too. One of the neat ones is what's the human level, right? Kind of like game days. So SafeStack Ava is actually it's open source package which does simulated spear phishing email attacks on companies, right? So it generates emails that have links which basically go in and let you and say, hey, you should click on this link for this special offer thing. And if you click on it, it says, no, bad person, don't click on links, right? So at Netflix, we used to get these emails that were the the security team would send in, and they used to leave USB keys lying around in the cafeteria, and if you plug them in, again, says in bad person, you're not supposed to do that. You're supposed to, if you find a USB key lying around, you should not just plug it into a random computer. So you have to condition the people, right? This is part of one of the weak links in the system. And there's a bunch of other tools here and a few companies doing stuff. So these are the 4 layers, the 2 teams, and the attitude here is you're trying to break it to make it better, right? So let's think about risk tolerance. So who is at risk for what, and what kind of risks are you trying to guard against? And you can kind of choose a little bit here whether downtime is a bigger risk than getting the wrong answer, right? Do you want consistency and security, which means that you have to be able to stop if you can't guarantee. This is the kind of the CAP theorem, right, basically. If you can't guarantee the state of something, the only safe thing you can do is just stop the system, and that's downtime. And that might be the right thing to do if your mistake could cause, $1 trillion to go to the wrong place or something, right? You should probably just stop and make sure that the system comes into a state where you can safely do the next thing. But in other cases, the biggest challenge, the biggest risk is downtime. And you can actually provide a degraded service, which is actually fine. So you want to be more permissive. And one of the things, again, going back to my time at Netflix, one of the hardest things was to teach people about permissive failure. And conceptually, this is, if it's our fault that we can't tell whether you should be able to do something or not, then we should let you do it, right? If we're not quite sure if you're a customer in good standing and you're trying to watch a movie, because of some failure in our system, we should just let you watch the movie, right? Because it's our fault, right? You probably are a customer in good standing. So if I just can't tell, most of the time you are, right? The probability that my downtime occurs at exactly the same point as someone fraudulently trying to get into the system is vanishingly small. So you want to be permissive on failures most of the time, right? So if you can't renew a ticket or there's some security system that's in there, you got to look at what is the actual cost of giving away the thing that you're currently trying to protect, right? So that's the concept here. It means you can build much more available systems. It's a really powerful technique for coping with partial outages of various parts of the system. Another thing is this incident life cycle. Something's gone wrong. What are you going to do? You want to try and mitigate what's going wrong so that it doesn't spread. You want to restore the system into some into some working state, and you want to adapt the system so that it doesn't do it again, right? That's basically the cycle. And that's kind of the anti-fragile feedback loop. If you read the book Anti-Fragile by Nicholas Taleb, he has lots of good examples of like working out. So you go to the gym to work out. If you work out too hard, you'll actually break something and end up in hospital and not be able to walk the next day. That's too hard, right? If you don't go to the gym ever, and then you have to run to catch a plane or something and you have a heart attack, that's probably a bad thing too. So there's a level of working out which is good. Level of exercise, most people have too little exercise, right? I know I do, but the running for planes is probably my main exercise at this point in my life. But you want enough exercise that you get slightly stronger each time you do it. That's the right level of exercise for an anti-fragile system, and that's what we're trying to do with chaos engineering, is introduce enough that we don't break the system. So we're trying to break it to make it safer. And there's a bunch of research and things on here, and this is actually, like, because I said break it to make it better, but really we're trying to make it safer. And safety there's a whole lot of stuff going on in safety, and there's this whole area about the new view of safety. This is about industrial safety. This is people operating nuclear power plants and heavy machinery and industrial processes. And what do you do when people die or get hurt or something goes wrong? And Todd Conklin is one of the leaders in this space. He does training classes, but he has a really good podcast called the Pre-Accident Podcast. If you want to know more about this area, go listen to this podcast, add it to your podcast list. Really interesting. He used to be the safety guy at the Los Alamos lab in New Mexico, and he's still based down there. So he knows all about stuff like that, big nuclear issues. So So that's interesting. I actually went on that podcast once and did a talk about 2 years ago about the chaos monkey and that whole idea, and it was he was quite interested in it. So it's not just industrial. Every now and again he has software people on. So John Allspor's been on there. In fact, John Allspor introduced him to me, and John Allspor has left Etsy, and he is now doing a whole bunch of work in this space. And there's a thing called the Stellar Report, and its URL is stellar.report, because that is actually the URL, okay? And it's a whole discussion about how to build safer systems and how to deal with the failure modes and reporting and things in this space. And really the core ideas I got from this was from reading Drift into Failure by Sidney Dekker, and that's a really good book to read unless you're on a plane or you have a loved one in hospital. Most of the examples are extremely disturbing. I had to put it down once sitting right on a plane because it's just full of plane crashes and people dying in hospital. But anyway. But it's one of the inspirational books, and Sidney Dekker is one of the inspirational figures behind this whole area. So I think this is a new emerging area, but this is the core concept. A failure doesn't have a root cause in a component failure or a human error. Right? If a component or a human error causes a system failure, it's a failure in the system. It's not a failure of that human. Like, humans do bad things all the time and systems don't fail. Just because this one time you did that bad thing, it actually tipped it over the edge. You shouldn't go and fire that person or replace that replace that component. It's because there wasn't enough margin. So the point here is you're trying to build systems that have a safety margin which is capable of absorbing human error and absorbing failure. And so the question then is, how much margin do you have? And here's a little example. If you're blindfold if I was blindfolded up here, right, on the edge of a cliff, I would be going like, okay, I think the edge of the stage is here. Okay, I can feel it. All right, that's where the edge is. I can back away from that a bit, right? So I've just established a safety margin of about 4 feet, right, in that dimension. I could go that way and feel my way over there and discover this, okay, I have a fairly reasonable amount of margin here, right? That's what we're talking about. And then I can fall over, or I can sort of take a step this way, and I know that I can take a step this way, right? Because I've established I have a margin to do that. So that's the concept we're trying to get here. I was trying to come up with an analogy for it. Hopefully that works. So this is the hypothesis that we're going. We think we have a safety margin in a certain dimension. Like, we could take 50% more traffic and we'd be fine, or this service could fail, or this thing could go wrong, and we'd still be up. That's the safety margin. So we think that, so then we carefully test it by like pumping, moving traffic from somewhere else, or overloading something, or pushing something up closer to that limit. And if you notice things actually falling over, like I find the edge of unexpectedly find the edge of the cliff earlier than I was expecting, I stop quickly and back out, right? That's what we're trying to do. We don't want to cause an issue. So then this came up in the panel session earlier. So how do you select a test? There's so many places you could inject failures. What are these dimensions, and where should you be trying them? Lineage-driven fault injection was a talk 1 year ago at QCon here. There was a talk about it by Colton and Peter Alvaro. It's a really fascinating idea, which is that you track, effectively, you trace from your edge, you take your business transactions that matter. Say in Netflix case, I pushed play, or I'm signing up for a service, the sign-up flow. You just follow the path, right? This is an important business transaction. What is the lineage of that transaction? What's the dependency chain? And you just work your way through that chain, injecting faults into that chain in a way that you're trying to make sure that that business transaction is going to work. So you're not testing everything at random. You could kind of call it fuzzing, right? When you just throw random things. It's probably good to do some random injection, but this lineage thing is that you're trying to find a key piece of business traffic that you're looking at, and then you try to inject faults into that place to make sure it doesn't go wrong. All right. So to summarize, what we really want to have then is really experienced staff who have been on maybe you don't have real outages. Planes don't crash every day, but pilots are trained in what to do if there is an incident, right? So that training is really important. So you want your staff to be experienced in the processes involved in dealing with an incident. You want your applications to be robust, so you want to put them in test environments and simulate failures in various kinds, and you want to do that in production too. You want a dependable switching fabric, meaning you exercise all of its error handling failure modes, code paths, right? You know what it does in all these different circumstances. It may still go wrong because it's hard to test these, but if you aren't testing it at all, you're going to be really screwed, right? And then you want a redundant service foundation. All your services and all your capabilities, you want to make sure that you've got those distributed out. So that's what we'd like to have, and that's my cloud native availability model. So I've got a few minutes left for Q&A. Okay.
Excellent. Awesome. Any questions?
Hey, Adrian, with the permissive model, is there a chance that you are giving more rights to the root cause of the permission mode?
Sorry?
Is there a chance that you are giving more rights to the same people who caused you to go to the permissive model by breaking your system?
You're giving... I'm sorry, I didn't get the question.
So if there is a hack attack on your side,
if there's an attack on the system?
yes,
Yeah.
that made you just, you cannot authorize the customers.
Oh, authorizing it. Yeah, okay.
So now you allow people in without authorization.
Yeah. All right, okay. You're talking about that.
Can it cause this
Yeah. So,
never-ending loop?
you know, if you couldn't tell whether this is a valid customer or not, and they want to do something that's relatively cheap for you to give them, like, say, watch a movie, and your system is basically down that could make that decision, you must just let them watch the movie, because most likely they are like a good customer, right? So I think it's okay, but I mean, you don't want people to go in there and sort of, you know, move $1 billion to some other account, right? So there are cases where where you want to put the hard control in there and you want to just stop the system, right? But I think in most cases, people tend to err on the side of blocking if they can't be sure, whereas they should actually think through, could I be more permissive in this failure? You want to log that you did it, then maybe you'll do some fraud analysis later to see if you were exposed. But there's a good paper by Pat Helland called Memory, Guesses, and Apologies, and this is the apology phase, right? And it's like, I couldn't figure out what to do. I'm going to punt you to customer service, or just like say sorry, or just try and deal with it. Okay, another
question?
Anyone out there?
Thank you for the talk. I just wonder, can you clarify what you mean by turn off the service for saving utility bill? Is that what you meant?
Yeah.
For hardware like servers.
Yeah, well, what I mean by turn off, I mean you could save power in a data center by powering them down, but that's what I meant was on a cloud. It's cloud native, right? So what I meant was just stop using them, deallocate the resource. You auto scale down, right? So I have 100 machines, and the load traffic halves. I run it on 50 machines. But I keep all the machines busy by shutting them down. And if you've got a QA environment, there's 168 hours in a week. Hopefully you're not working more than about 40 or 50 of them. So you should be able to shut down your entire QA environment for 2/3 to 3/4 of the week, because there shouldn't be anyone using it, right? So that gives you back a higher utilization over time, right?
That saves your bill for
Yeah.
electricity. Is that
Well, it saves you bill. I mean, if you're on a cloud, you're paying by the second. So, right, you just stop paying for things you're not using. That was the point. Yeah. Another question? I want it back there.
Hey, thanks. So in your graphs, you had a lot of different connections between all of the nodes. How do you inject in between those nodes? Do you have to always have middleware in between all the different services such that you can throttle?
That's a good question. I think number of different ways of doing that. The Netflix way of doing it was to build a set of libraries. Basically, most of the Java-based services at Netflix were built from a template. You just started with this, base server that you copied, and then you added your own business logic to it. And it had a standard HTTP request handler, which had additional code that could inject failures into it. And then the outbound side where it made requests, again, there were hooks for injecting failures into it. So that's part of just you injected your business logic into the middle of this framework, which was a web server. It was a Tomcat server, something like that. So that's one way of doing it. If you use the Spring Cloud framework in Java, you can pull all those services in. Ribbon is the main one that Netflix has. A newer way of doing this is to use a service mesh. The Istio service mesh, which is now part of the Cloud Native Computing Foundation, uses Envoy, which is that's the actual service mesh point, and it comes from Airbnb, I think. No, Lyft. Okay, what's your mix? Yeah, Lyft. So what that mesh gives you a point where you can get in there and configure it to inject failures and things like that and do that stuff. So I think this is a property of the service mesh. Service mesh can be an additional process which is running alongside your server, where you're just sort of talking to local hosts to get to it, or it can be embedded in your application if you're using a library that supports it. I think with Java you can do some, because it's bytecode, you can do some injection of code to do things. So I think things like app dynamics, where you can inject the monitoring into an application that wasn't instrumented, or you could just hard instrument stuff. So there's a number of ways of doing it, but I think those are the common ways I've seen.
Great.
Yeah. You can do it at the network layer as well if you're going through, at the packet level as well, but it's a bit harder to coordinate that.
Time for one more?
Yep.
Anyone else? This is the precarious run down the side.
All right.
AWS itself, is it doing any chaos testing?
Yeah, AWS, Amazon has a chaos engineering team.
Right.
AWS does a whole lot of different testing, but we have the basic principles in there. We don't have a centralized team because each service team manages itself, but we do a fair amount of testing and.
Yeah, the reason I asked this question is that what's appearing to me is that most of the time, doing effective chaos engineering is a statement on complexity architecture, like how well you can understand and manage complexity, which is, I don't think is just contained in application layer, like it's up and down the chain.
Yeah. I get it's off into a much more philosophical question, but I think the point here is that if most systems right now are so fragile that if you poke them at all, they fall over. I think that's kind of the normal case. So if we just get incrementally better by training the people in how to deal with it is the starting point. Right? If you just exercise people so they know what to do during an outage, start there, and then start getting individual applications. If you've got to microservices, you've now got a bounded context that does one thing. You can start reasoning about it. You can say, what happens if that one thing does something wrong? You can you can inject failures into that one service, see what happens. You just work through your system. So there are still systemic problems that will occur, right? If you've got your timeout set wrong, you'll get congestion collapse, you'll get thundering herds, you'll get all kinds of other larger scale problems, and you need to test for those as well. But yeah, I did a talk at Craft Conference a couple of years ago where I talked about some of the issues like timeouts and stuff like that. So, by the way, if you want all my slides on microservices, they're on my GitHub account, Adrian Cockcroft on GitHub. There's a slides thing and a big file there, a few hundred slides worth of stuff. All the things up to about a year ago when I joined Amazon, that whole deck's there. Okay.
One last question. Is there a point when chaos engineering could turn into a DDoS attack towards the whole system? Like when does that occur? How do you make that balance? How do you make that decision that we should not go further?
You have to, if you're doing it right, you should be monitoring the system so that if it starts to look bad, you back out. And hopefully by backing out, it stops. But you can tip a system over. There's hysteresis. There's classic cases where systems aren't restartable, right? If you actually take your system down and back up again, it doesn't come up again. That's a common property of systems that have grown over time. Like the system only works if the caches are warm, for example. So you have to, if you kill your caching layer, then you can't rewarm it, and then you're down, right? So you have to be pretty careful about some of these properties. But it's good to know that, because then when you do it during the day when everyone's there and watching, rather than 3 a.m. on a Sunday or something. One of the, I got one more Netflix thing, which is that the most annoying thing about Netflix was that it would tend to break at 7 p.m. on a Sunday night, because that's when everybody wants to be at home watching TV with their kids. is that's the problem, that you're sitting home watching TV and then it goes down, because that was the peak traffic every week. And when you've got a week-on-week growth rate where every week is an all-time record, like having the peak be an off time is a pain. So you want to create enough chaos during the week on a Wednesday when everyone's at work and everyone's fresh. That's the model where that's when you want to be exercising the system. You don't want to be doing stuff out of hours and having a bunch of people with sleep deprived trying to make important decisions is always a bad recipe for these things.
I think the thing I'd add there as well is one of the principles of chaos is containing the blast radius. And so one of the ways you prevent DDoSing yourself is you start small. What's the smallest thing that can teach you something? And then as your trust and confidence in the system grows, you grow it. So eventually you're running at production scale, but you're not starting there.
But if you poke one back-end database and you've got your timeout set wrong, it could ripple all the way through and tech out everything. So it's going to happen one day. You should do it live. Do it when you're ready for it. Okay. I think we're out of time. So thank you everybody. Thanks for coming.
Thank you, Adrian.